Welcome back. In this lecture, we are going to introduce the space of continuous function, that is, a topology in the space of continuous functions. So let's begin with the definition of a limit in a topological space. Okay, so today's lecture will be kind of quite basic. So if x and y are two topological spaces, and if f is a function from x to y, then you say an element of y, L, is called the limit of f at an accumulation point x naught in capital X if for every neighborhood v of L in y there is a neighborhood u of x naught in x such that f of u is contained in f is contained in v. This is the definition of limit of a function. So as x goes to x naught, f goes to f approaches to f approaches L. So in particular, if x and y are metric spaces with the respective metrics d1 and d2, then the definition of limit is precisely that for any given real number epsilon, there is a delta such that d2 fxl is less than epsilon for all x whenever d1 x comma x naught is less than delta. Now if the topological space Y is Hausdorff, then the limit L is always unique. Now what is a continuous function? So if you have two topological spaces X and Y, and if F is a map from X to Y, we say F is continuous at any point x naught of capital X if for any open set U contained in Y, which is an open set which contains f of x naught, then its inverse image under f, that is f inverse of u, contains x naught, obviously, right, because it's the inverse image of that, and that set is open. So for every open set containing f of x naught, its inverse image is an open set containing x naught. Whenever this happens, then you say f is a continuous function, that is, inverse image of open sets are open sets. In particular, if x and y are metric spaces with the respective metrics d1 and d2, and if we want to say if f from x to y is continuous at x naught, if for any given real number epsilon there is a delta such that the d2 metric, that is in the y space, the distance between fx and fx naught is less than epsilon for all x which are of the distance less than delta from x naught. Now if one can choose, so for given any epsilon you get a delta, right, such that for all delta neighborhood around x naught, the function, all the image points are in the epsilon neighborhood of f of x naught, right? So if you can choose this delta independent of x naught, so here you see this delta depends on epsilon and x naught. So you are looking at the continuity at x naught and you are fixing an epsilon, so the choice of delta can depend on both epsilon and x naught. If you can choose a delta which is independent of x naught, that is for every choice of an element in capital X, the same delta works, then you say that the function is uniformly continuous. Now we denote C of x as the C of x denotes the class of all real valued continuous functions on the topological space X. So if X is a topological space, then C of X is the set of all functions, set of all real valued functions, that is set of all functions from X to R. Okay, so this is the set of all class of all real valued functions, real valued continuous functions defined on X. So domain is X. Okay, so if the X is a topological space, okay, in other words, we are just renaming it X as K. So if the domain is a topology, so it's a compact topological space, then one can give a norm on this space. First of all, you can check that it's a vector space and so on, but I'm not getting into that. So this is for C of X will actually be a vector space. It's obvious to check and check that because sum of two continuous functions is continuous, and any scalar multiple of a continuous function is continuous, right? So C of X forms a vector space. Now, for the special case when the topological space, that is the domain, is a compact topological space, then you know from the topological result that every continuous function on a compact set is bounded. So using that, one can define the notion of length or norm in the space of continuous functions, which is defined as norm f is supremum of mod fx, where supremum is taken over all x in the domain. And because it's a bounded function, this is a finite quantity. Okay, so this is the norm of the function. This norm is usually called uniform norm or supremum norm. Now using this norm, you also have you can define a metric, right? So this is called the uniform metric and so on. And this metric induces a topology which is precisely the uniform convergence topology. So whenever you say a sequence of functions converges to, let's say if fn converges to fn converges to f, then convergence under in this norm or in this metric, it basically means that it converges uniformly. That's by definition here, right? Because you're taking supremum over all the arguments here. So let's look at this notion of pointwise convergence and uniform convergence. So as I said, the norm that you give in the space of continuous functions is the uniform convergence norm. I mean, that norm induces the uniform convergence topology. Whereas, but C of X has actually both the two topologies. One is the pointwise convergence topology, and the other is the uniform convergence. There's a topology that induces pointwise convergence, and there's a topology that induces uniform convergence. So you say a sequence of functions converges pointwise if fn of x is equal to f of x for each x. So the convergence happens for every x in capital X. In other words, if you want to use the definition, for every epsilon and x fixed, there is a positive integer capital N, such that for all little n bigger than or equal to capital N, fn x minus f of x is less than epsilon. So this inequality is valid for all n bigger than n. So this happens for each x. So this is the pointwise convergence. Now if you can choose this n independent of the x, that is for every x in this, if you can choose the same, you can choose the same n works for every choice of x in capital X, then you say that the convergence is uniform. Okay, so that's what uniform convergence means. So this n, for every epsilon, the n that you obtain, which in general depends on both x and epsilon, now is independent of x, then it's uniform convergence. So as a simple exercise, please try doing this exercise. First show that for any real number um, lying between 0 and 1, including 0, um, and for any positive integer n, I mean, when I say n, so the n goes to infinity. So the sequence of so set of all positive integers. So you fix an alpha which is between 0 and 1, including 0. Then alpha power n always converges to 0. Please do this as an exercise. Okay. So if you prove this, then consequently you also try to show that if you take the n degree polynomial x power n polynomial, this is a continuous function. We know this, right? We can show that this is a continuous function. Now this function is defined on the interval 0 1, and it will converge pointwise to this function f, okay, which is a discontinuous function. So show that sequence of this function. So for each fixed x as n goes to infinity, for each fixed x, this goes to f of x. So this converges pointwise to f of x. Whereas this function is continuous in 0 1, while this limit is not a continuous function in 0 1. So basically pointwise convergence does not preserve the continuity. Okay, but that's not the case with, so that's what I'm saying here. So as you've seen in the example above, pointwise limit of a sequence of continuous function can be discontinuous, as we have seen in the previous example. Whereas if you take a sequence of functions, continuous functions, which converges uniformly to f, then the limit has to be continuous. So the uniform convergence preserves continuity. So proof is very easy. So let's just quickly recall. By uniform convergence, for any epsilon, there is an m such that this happens for all x. So this m that you choose is actually independent of the choice of x you have. That's what uniform convergence means, right? So you have this inequality for all x in capital X. Therefore, now for any x naught in capital X, if I choose fx minus fx naught, then by triangle inequality, so you add and subtract fm and fmx, and you add and subtract fmx naught. So by triangle inequality, you get this 3 inequality. Okay. Now here this fm minus fm, f minus fm of x, which is this quantity, is less than epsilon by 3. Similarly, this last term fmx naught minus f of x naught, this is true for all x, right? So in particular is also true for x naught. So you have this also as epsilon by 3. Okay, so the first term and last term both are less than epsilon by 3, and each fm is given to be a continuous function. Okay, so you use the continuity of uh, fm at x naught. So then you you can show that this is also less than epsilon by 3. So you have a delta such that this is less than epsilon by 3. Okay. If you use the fact that fm is continuous at x naught, you can show that this is less than epsilon by 3 for some delta. So for all x in a delta neighborhood of x naught, we have this result that this is less than epsilon, which means we have shown the continuity of f, right? When you have to show f is continuous, you just need to show for every epsilon there is a delta such that this is less than epsilon, and that's what we have shown. This quantity is less than epsilon in a delta neighborhood, and that delta neighborhood actually comes from the continuity of fm. from this, what have we observed is that the space of continuous functions, sorry, that's a mistake, this should be K, CK. So in a compact topological space, you have a norm, and that norm was the uniform convergence topology, and under uniform convergence topology, this is a complete space. This is a complete metric space. In fact, it's a complete norm space, right? So C of X is a Banach space. So what we proved here is actually implies that the space of continuous function on a compact topological space is a Banach space. So I'd like to propose this exercise. Please try doing this exercise. We might need it sometime later. So if I is a closed bounded interval of the real line, and if you have a sequence of functions fn defined on I, which are monotonous continuous functions, okay, and they converge pointwise to a continuous function f. Okay, so a priori you know that the limit is a continuous function, then the convergence is actually uniform. Okay, so if you have a monotone sequence of continuous function converging pointwise to a continuous function, then the convergence should be uniform. It's actually uniform convergence. Okay, please try doing this as an exercise. We might need it later, so do it and remember this result. So now the question is, we have defined the space of continuous functions and defined the norm for a compact topological space, and we have also seen that it's actually a Banach space, a complete norm space. What about continuous functions on non-compact topological spaces? So if you don't assume this compactness, what is the kind of, because if you remember the notion of topology, the notion of norm was dependent on the fact that the domain was a compact set, because only then the norm will not become infinity. It's a finite quantity because you were in a compact topological space. So what if I start with an arbitrary topological space which is not compact? What happens to C of X when X is not compact? What kind of topology can you give? So one way of doing this is that suppose I start with an arbitrary open subset omega of Rn. Okay, so it's an open subset. It's not a compact subset of Rn. So it's an open subset. You know that you can write this open subset as a countable union of compact subsets, right? You can do this, right? For instance, let's take Rn, or let's take R2, for example. Whatever we do it for R2 or even Rn, even R will work for Rn. So let's take R for instance. You take any open set. Now you actually see that, take R itself. Let's look at R itself. R itself is a countable union of intervals. Let's say minus n to n. So, or in this notation, you can say take kj to be minus j to j, closed interval. Okay, minus j to j. Now that's a compact set, and the union over j will actually give you the entire real line. So in fact, if you take any open subset of the real line, it can be written as a countable union of compact sets, right? Just by intersecting the minus j comma j to omega, you will get the compact sets. And this compact sets has this property that they are nested, right? So the kj is contained in the interior of kj plus 1. So this property is actually called the sigma compactness of omega. Okay, so you can write the open set as a countable union of compact sets. So you start with any open set, you have this property that for the Euclidean space, every open set has this property that you can write it as a countable union of compact sets. Which means if I look at the space of all continuous functions on the open set, let's say C of omega, one can think of this as countable union of continuous functions on Kj, right? Because K, so you have functions with the domains Kj and union over all functions over Kj is going to give you functions C of functions defined on omega. In fact, it will actually have more functions than those functions. So what you do is that you look at the space of a continuous function. What we are interested in is what kind of topology can we give here, because the uniform norm or uniform metric doesn't work here, because you can have unbounded functions here. This is an open set and it's a continuous function. You can have unbounded functions here, so that quantity supremum, the uniform norm, can blow up. So what you do is that you define this semi-norm. If you don't define a norm, you can define a countable collection of semi-norms, that is corresponding to each compact set Kj. You can define a semi-norm. That is how you take any function phi, okay, and the semi-norm of phi is defined as supremum of mod phi, because phi restricted to Kj, because Kj is a compact set, should be bounded. So this supremum over Kj is valid, and this you can do for each j, right? This you can do for each j, which means that you have a countable collection of semi-norms. Please show that this is a semi-norm. So we have already seen this is the same definition we use for compact set. So it was a norm there. In this case, it becomes a semi-norm. Please verify that. Okay. So by definition, you notice that P0 is less than or equal to P1, because P1 is supremum over K1 and P2 supremum over K2, and you see that K1 is contained in K2 and K2 is contained in K3 and so on. So the supremum that you are taking is actually over a bigger set each time. So supremum over K0 is smaller than the supremum over K1 and so on. So you have this inequality for these numbers, semi-norms, for any value phi. And this, using this semi-norm, you actually can say that this set of all phi such that pj phi is less than 1 over j. This collection of j actually forms a local base for C of omega. Okay, this can generate all the open sets locally, neighborhood basis basically. Now you must have seen in your course in metric spaces the advantage of this kind of a metric. So using this semi-norm, one can give a metric in this space C of omega. That is, the metric is given by this. Either you take max or you take sum over all j. Okay, whichever is. Okay, so this will be a convergence series by definition. Here you see the numerator is a quantity smaller than the denominator and so on. So this is, you can check that this is a well-defined metric in C of omega. Once you have a metric, you have a topology, right? So, and this metric is defined by this countable collection of semi-norms. So we will not do it in this course, but I mean, you can do it as an exercise. That's what I mean. I mean, you can refer books and find exercise. So prescribing this metric in this space of continuous functions on omega, C of omega, can actually show that this metric is complete, and this is actually a Frechet space. Okay, C of omega is actually a Frechet space. So please use this opportunity. If you don't know these stuffs, or you have not seen this before, use this as an opportunity to go and kind of read about it or refresh it and so on. Okay, so I am just doing this to help you recall these results if you have already seen it. If you have not seen it, use this opportunity to go and read it. Okay, something like maybe the Rudin's functional analysis book might have these things. So this metric, under this metric, the C of omega is a complete metric space. In fact, it is actually a Frechet space. Okay. Now this and the topology that is induced by this metric is precisely the uniform convergence on compact sets. Okay. So you see that the way the semi-norms are actually defined on the compact sets, which is actually the uniform convergence on the compact sets here, or it's also called the compact open topology. Okay. So we have seen the notion of continuous functions in this lecture. I mean, the space of continuous functions in this lecture, the topology that you can give when the domain is a compact set, and and then it becomes a Banach space. While when the domain is a non-compact set, but it's an open subset of an Euclidean space, then it actually becomes a Frechet space and induces the uniform convergence on compact sets topology. That topology. So there is one well-definedness that you need to verify here. So I leave it as an exercise for you to check that the topology that you obtain here is independent of the choice of compact sets that you choose in this. So this representation of writing an open set as a countable union of compact sets, this is not unique. You have more than one choice of a collection of compact sets which whose union can be omega. So if we are going to define the topology dependent on the kj, you should you should be able to check that the definition is well defined, that is the topology is well defined and is independent of the choice of the compact sets that you choose here. So this is called the exhaustion by compact sets. So whatever choice that you have here, the topology will not change. Okay, I'll try that also as an exercise. Okay, we will stop here. We will meet in the next lecture. Thank you.